Thank you, Jerry. As I said, I'm Jane Annear from Concurrent Technologies, and I'm based out of the UK. And also, as Jerry said, Glenn was going to be here, but he had an argument with a football, and we'll leave it at that. He'd have his own stories for you when you see him next. For those of you who don't know us, Concurrent Technologies manufactures hardware, so we're designing for VME, VPX, Compact PCI, and AMC products. And what I want to do today is just to take you through some of the challenges that we see with our customers as we try to take advantage of the high-performance computing technology that's out there and try to bring it into the embedded world. So, having gone last today, I realized how many presentations have mentioned the Internet of Things. There's probably not many that haven't. I arrived here on Saturday night, and I think within an hour, I'd seen a TV commercial mentioning the Internet of Everything. And it was interesting today to hear about the different definitions of the Internet of Things, or IoT. So, so I'd been here not very long, and I'd heard about the Internet of Things and the Internet of Everything. We've heard various presentations today with a definition, which was very interesting. And I think Ray's disappeared, but I think Ray's got his own definition of the IoT, which perhaps he'd want to elaborate at some point. But no matter what we think, and obviously Jerry's very excited about the Internet of Things because he's obviously planning to buy lots of connected devices. One thing that took me of interest was the fridge. And I've seen before this application where you can be away and it will determine how much beer you've got in your fridge and send your order off for you, so you'll get it stocked by the time you get home. There might be a word of warning there, though, that if that's connected to your health physician, you might get a similar warning back to say you're not eating very healthily and here's your increase in fees. So just a little warning of some of the things that could happen for you. But no matter what we think of the Internet of Things and all the forecasts about it and all the hype, it still remains that we have the capabilities today to collect a lot of data, analyze a lot of data, store a lot of data, and we're, in our customer base, are finding that more and more people would like to have that stored perhaps or analyzed back at the edge where you really need it real time. So this is really going to compare some of the differences between the supercomputers that you see out there. And what we're trying to do is to talk to customers who want applications there right in the minute. So you've got very fast remote data being captured. So if we look at these supercomputers, which is the alternative, they're large. This is a typical one from a university in the UK. They're just many, many boxes, all connected in a parallel system, giving you lots and lots of computing power. Because what they don't have to worry about is the size and weight and all the other attributes that an embedded system would want. That's not talking about, if you look at the list of the 500s, largest supercomputers, it'll give you some interesting reading on just how much compute power is there. More importantly, how much power it needs to actually maintain those and the logistics behind them. So how can we leverage and learn from these supercomputers but bring it back into the edge where our customers need it? So if we look at what we need for our customers, it's not surprising to see these with size, weight, and power, obviously very important for us. We need it to be rugged. We need to consider the environment these are being stored in. Again, not surprising, this is what's driving our technologies like VPX. This is all the things that went into those standards. And again, if you want to bring this back into the edge, you've got to think about, it's being brought there for a reason. So we want it in real time. It's got to be deterministic, and it's going to be fast, low latency, real-time data. Because if you don't have that requirement on the application, you can probably do it back later on and get your data back later. We shouldn't forget either, in the course of a fairly short space of time, how far we've gone in terms of hardware. If you think back to VME, parallel buses, we had single-core processors. So while they were doing a great job, if you think about what we have today with all the serial fabrics, so you've got now VPX, small form factor, AMC, and you've got these multi-core processors. So the whole complexity of what we can build in terms of hardware is way different from not many years ago. Gives you a lot of choice, but now you've got to think about how that's going to connect together. And we heard earlier on that the complexity of some of the serial fabrics, it's great, and it's bringing it all in and making it all smaller. That's what's giving us that capability. But you've also now got to think about more about the software and who's going to program these systems together. So just looking at a typical, perhaps a backplane, serial backplane, this happens to be VPX. What you can have now is very specialized processors. So this one's showing lots of processor boards, a switch, and you've got maybe an FPGA in there, and a disk for storing. So this is all mainly connected by PCIe in this case. But you notice that there's also a link in there. Two boards are linked by rapid I/O, and there's another board link there directly linking a disk and a processor. So now we haven't got a nice standard system of all one bus. You've got complexities of different protocols coming into this as well now. That would probably be a standard backplane, but this is also what's allowing us to shrink this down so we can get our size, weight, and power down. But how do we tackle the software applications, and how do we take advantage of all that ecosystem that's out there from the supercomputers? So the interconnect between servers, as I said, it's pretty standard. They're expecting it probably to be Ethernet, and you're probably going to be running Linux, and it's TCP/IP sockets. And if you're an applications engineer designing for the supercomputers, you can take advantage of that ecosystem, but you are expecting somehow not to really see that hardware at all. It's transparent, and it's transparent because of that Ethernet link and that choice of TCP/IP. So if you want to run something like Hadoop, or to distribute your system amongst many computers, you're going to be expecting to see perhaps the standard Ethernet link underneath there. That isn't what I just showed you when we put that VPX system together with its PCI and its rapid I/O and all the different protocols that were going with it. So whether it's Hadoop or whether you're going to buy from the ecosystem of a standard weather monitoring system, there's loads out there. But they're all going to be basically the same and basically expecting that same underlying system. So the challenge is, how can you do that? What's the solution? And one thing that we came up with was a middleware product that we called FNS, which is Fabric Interconnect Networking Software. And it's an optimized layer, middleware. And what it's doing is actually shielding the hardware that we saw in that VPX backplane, so that you can now take the standard applications like Hadoop and run it on this system, and it's totally transparent to the hardware underneath it. So you can have your PCI Express, you can have your rapid I/O, and your application is now just totally removed from that hardware. Sorry, I didn't move on. So FNS is actually emulating the Ethernet device. And as I said, it's removing you from the hardware complexities that we just built into the VPX backplane. And what we did was to prove this was to run some comparisons between a 10 gig Ethernet backplane, a rapid I/O backplane, and a PCI Express backplane. And I'll show you some of the results that we got from that. But just to explain FNS a little bit more, you'll see on that slide that the hardware is at the bottom. FNS sits in a layer with the operating system. And the application, where the application engineer is interested, is way at the top and totally removed from the hardware complexities at all. So now you've got a very optimized hardware solution, and you've got this layer that will allow you to use all the ecosystem that's out there for the supercomputer applications. So the tests we were running, as I said, they were split between three backplanes, or Backplane technologies: 10 gigabit Ethernet, PCI Express, and the rapid I/O. And we set that up as far as possible so that they were equal, and we were running third-generation processors to do this in the systems. So some of the things we said that were important to our customers was obviously the throughput. And you can see here that as the packets, this is fairly obvious, but as the packets get larger, we're getting better throughput. And you can see Serial Rapid I/O and PCI Express tending to win out at the top. Again, this is not about choosing a fabric. We're not recommending a fabric here. The whole point here is that it's transparent to them. They can pick the fabric that they want to do the job at any point in that system. This is just showing you can do that. But we did have to take care that obviously the CPU utilization itself didn't get swamped. And again, this is showing that with the larger packets, we can be down at 5% utilization on a processor as the packet size increases. So again, we've got good use of the CPU, and that's now free for your application. And latency, again, this is just showing the differences between the buses, but again, I stress, this is not recommend any particular bus. It, again, is showing you can pick the one you need to do the task. Not surprisingly, Rapid I/O was coming out very well here, but then that's a known fact and why people use Rapid I/O as their backplane as a choice. This just shows you some of the implementations we've made using this. The one on the left is AMCs, so in four AMCs in a system. That's a Rapid I/O backplane. And this was done for a 1U DCCM box. It's just a proof of concept. We've used 4, their third generation Intel processor boards, but equally well, you can scale all of these up to no matter what you want to do. And the application on the right is using a VPX system. So we put a starter box together. In this case, again, another 4 processor boards there, and this one was using PCI Express. Then I come back to the point that really what we're saying is you can run Hadoop on either of these, and you don't have to make changes to the application. So it's now scalable and portable, which is just what they want from the supercomputers, but you've now brought it back into an embedded computing, and you've got it on site. So just to summarize, what we were showing here was the building blocks and the complexities of moving some of the applications from your supercomputers back into the embedded world. So you've got local processing to the place where you need it to be for very high performance analysis of a battlefield or any application where it needs to be real time. And this was just one solution that we came up with. Thank you.